The general method for computing determinants is the expansion by cofactors method, which in principle you could apply to 4 by 4, 5 by 5, and so forth. Well, let's start with an example, because without an example, there's no point in talking. You got to see an example. Okay, the method works for square matrices of any size, but it's much harder for much bigger matrices. All right, example. Now, in fact, this is the same determinant, or well, the same determinant that we were talking about earlier, right? The same 3 by 3 matrices here. We already found out it equals 10. So if you do this right, you're going to get 10. Okay. So here's the idea. We're going to choose a magic row or a magic column. That's not what they're really called, but let's be cute, to expand along. Okay. We call it the expansion by cofactors method. Expanding, we pick a magic row or column to expand along. And you can, in principle, take any row or any column, but preferably one with zeros, because zeros really help a lot, as you will see. So in my example here, well, the best choices would be probably either column 1 or row 3. Here I choose the first column, column 1. So let's call that our magic column. Again, not really what it's called, but let's be cute. It helps. That 0 will help us a lot, as it turns out. Okay. And by the way, I'll call these the 3 magic entries. The 3 entries of our magic column are the 3 magic entries. Again, I'm being cute. Now, we've chosen the first column as our magic column. We could have chosen the magic row as well. Now, it's going to help to write out the corresponding sign matrix, at least the signs corresponding to the first column. The way that the sign matrix works, and we will need this later on, is that you're going to have plus signs on the main diagonal, and then you checkerboard, you alternate. Every time you move either right, down, up, or left, you're going to alternate sign. So here it's plus, minus, plus. We can take a walk, minus, plus, minus, plus, minus, plus. No 2 neighbors are the same sign, and it will always be plus signs on the main diagonal, not necessarily on the skew diagonal. Well, I guess we can't talk about a skew diagonal here, but this is like the longest skew diagonal. Yeah. That's not always the case. For example, in a 4 by 4, you'd have a minus up there. All right. We're going to need this thing later on. And again, since column 1 is our magic column, we're going to focus on these entries here. In fact, you could even erase the rest of this. You just need the ones here. Plus sign up here, it's on the main diagonal. Plus sign up here, then alternates minus plus. In general, the formula for the sign will be -1 to the I plus j, where I is the row number, j is the column number. Of course, a -1 corresponds to a minus, a +1 corresponds to a plus. Right. Here's a sign matrix for a 4 by 4. Here, the skew diagonal is, in a way, the longest skew diagonal, kinda, is all minuses. And it will be the same sign, either all pluses or all minuses, because you alternate here and here, for example. Again, here's the general formula. All right. Circle this again. I'll circle this too. All right. So now we're going to do expansion by cofactors or by minors. So the minors are going to correspond to the determinants of smaller determinants that we'll be working out. A cofactor would include the sign from the sign matrix. All right. Now, in the cofactor expansion, you're going to have one term corresponding to each of these magic entries. If an entry is a 0, then it's automatically 0. The term is automatically a 0. That's why we love 0. And if you have a row, if you have a row or a column of all zeros, the determinant is automatically 0. So if we had something like 0, 0, they look like 6s. So if we had something like 0, 0, 0 as our first column. I don't even care what happens in the rest of this 3 by 3 matrix. The determinant will be 0. But here, not necessarily, over here. All right, so the pattern goes for each of these 3 magic entries, not really him though, you're going to get a term. Each term consists of the sign from the Sine matrix, which we get over here, the magic entry, and the corresponding minor, which I'll explain later. The minor is the determinant of the submatrix, the smaller matrix that you get when the row and the column containing the magic entry are deleted. Okay, so how does that work? So it's right here. We're going to expand along the first column. Now, the signs from the Sine matrix, they go plus, minus, plus. So the signs from the Sine matrix go plus, minus, plus. The magic entries go -1, 3, and 0. I'm setting up this template. The submatrix is the hardest part. Here, I copy the 3 by 3 matrix here and here, which may be overkill, but I want to show you what's happening. The idea is that you should be able to do this problem without having to write the entire matrix out, but I want to show you what's going on. Okay, so for this first minor, for this determinant here, we take the original 3 by 3 matrix and we delete the row and the column containing the magic entry we're looking at. We're looking at -1. The -1 goes here. Over here, we cross out the row and the column containing the -1. And we take the determinant of this submatrix. Then we have a minus sign times the 3 here. That's our next magic entry. Times the determinant of, we delete the row and the column containing the 3. We're always going to delete our magic column here, by the way, because it contains the magic entries. And we'll take the determinant of this submatrix. Plus 0 times, well, who cares anyway? I mean, it'll be some number, but this product here will be 0. And the term here will be 0. All right. So now we're down to these. I've cleaned these up. So now we have to find the determinant of this 2 by 2, which reminds you of butterfly. The product along the main diagonal minus the product along the skew diagonal. -2. Again, personally, I like to write products instead of writing too much out, but -2 minus -1. 1 times -1 is -1, right? -2 plus 1 becomes -1. All right. Product along the main diagonal minus product along the skew diagonal. All right. Now, over here, product along the main diagonal, -1. Minus product along the skew diagonal, 2. And that's -3. All right, let's bring it all together. -1 times -1 minus 3 times -3. And by the way, the fact that these numbers look a lot alike, it's a coincidence. It's not always like this. But the answer is 10. 1 plus 9 is 10. The same as before, of course. And by the way, there is a way that you can use EROs to help you find determinants. You'll be taught that in Math 254, linear algebra. So for example, let's see, row replacements, the rescaling and addition method that preserves determinants. For example, if you add this row to this row, you get this all 0 row, and you know the answer is 0. Every time you switch rows, that leads to a sign flip. And you can factor a scalar, a non-zero scalar, out of an entire row or an entire column. There's like a factoring here out of a single row. But again, that won't be really in our class. You'll see these in Math 254, linear algebra. Again, if a square matrix has a row or a column consisting of all zeros, its determinant is 0, like this guy. And if you have a matrix in triangular form, either upper triangular or lower triangular, then the determinant is the product along the main diagonal. In this case, 2 times 3 times 4, or 24. Does not matter what these are. And it makes sense because if you were to do cofactor expansion, it would be plus the 2 times plus 3 times positive 4. 2 times 3 times 4. Now for this 4 by 4 beauty, normally a 4 by 4 would be very hard to do, but there's a clear choice for which row or column you want to expand along. Which magic row or magic column would you choose? I would choose row 2, otherwise it'll be a lot more work because there's only one term to really deal with here, which corresponds to the 3. But wait, I need the sign matrix, or at least the relevant signs from the sign matrix. Well, here's the thing. Now, in general, we're going to get 4 terms from this cofactor expansion because we have 4 numbers here, but 3 of those terms are going to be 0. This is the only one that's really relevant. What's the sign from the sign matrix? Well, we know we have a plus sign here. Along a diagonal, same sign, plus sign. So that means for the 3, you're going to have a minus sign. All right. So you will have to do a sign flip there. There's a negative sign indicating a sign flip. Or you can walk like this, positive, negative, positive, negative. Okay, so we have the negative sign from the sign matrix. The number here, the magic entry, the only one that's really relevant, the 3, and the determinant of the row, the submatrix you get when you delete the row and the column containing the magic entry. And you can attack this with either Saras's rule or another cofactor expansion method. Turns out this determinant's 2. Negative 3 times 2 is negative 6. Of course, work this out. Now, next up, I'll just have a brief discussion of cross products, which will not be on your homework or exams, but it's something that definitely comes up big time in calculus with analytic geometry 3, Math 252. More of the analytic geometry part next time.